Welcome back. In this lecture, we're going to introduce a new data structure called dictionaries. And we're going to follow the same trajectory that we did with the other data structures. I'm going to introduce the intuition behind the data structure. We're going to talk about how to implement it. And then we're going to talk about the algorithms on it. And then we're going to talk about the runtime complexity of that. And wherever possible, compare that back to the previous data structures. Okay. So by way of motivation, let's talk a little bit about find. So up until now, we've had two ways of searching for data. In an unsorted list, I just hand you a bunch of things, whether it's a singly linked list, a doubly linked list, a regular list, whatever it is, just find me something. And there we saw for the most part there's not much to do other than big O of n. Start at the beginning, go to the end, and that's all you can do. Now the other option was that we could sort. We went through all those different sorting algorithms, selection sort, insertion sort, merge sort, quick sort. And we could sort in n log n time and then find things very quickly because, for example, if we did binary search, we could find in log n times. So the sorting was a little bit expensive, but once something was sorted, we could find it relatively quickly in log n time. And so let's just, by way of review, look at all of that. So in an unsorted list, big O of n. You just got to look through all the elements. There's nothing to do. There's n elements in the list. I got to look at all of them. Worst case scenario is I have to look at all of them. And again, find in a sorted list is log n using binary search. But, and this is important, you still have to sort the list. And the sorting of the list, of course, costs O of n log n. So remember, we had a whole bunch of different sorting algorithms. There was insertion and selection. Those were n squared. But then we did merge and quick, and those were n log n. So this looks really, really good compared to this, but there's a little expense. Now, if the list is largely static, well, then sorting is not a big deal. You do it once, and then you get the benefit of searching all you want. But if it's extremely dynamic, well, then it's going to cost you a little bit more. Okay. Now, this in particular is what we have to worry about, is that insertion into a sorted list still costs me big O of n. Why? Well, if I have a sorted list, I've got to find where I want to insert something into a list. If it's in a regular list and I insert, well, I've got to move everything, and that costs me big O of n. Now, if it's not a list, but it's a singly linked list, we can do a little bit better. But everything here still is a little bit costly in terms of finding. And if finding is something that you have to do all the time, like many, many times a millisecond, and you have phenomenally large database, think Google, think Facebook, then even log n and n log n are going to be a little pricey. And what dictionaries are going to allow us to do is to do a little bit better than that. In fact, a lot better than that. So that's by way of motivation, is that when we are dealing with massive data sets, we need to be able to access things very, very quickly and add things and remove things from the database very, very quickly, and that's what dictionaries are going to afford us. So, by way of motivation, let's think about the following problem. I give you just a list, so this is just standard list, square bracket, comma, delimited, with a bunch of digits in it. So just numbers between 0 and 9, only 10 possible numbers, and of course there can be repeats of those. And I ask you to build a histogram of the distribution of the first 10 of the 10 digits, 0 through 9. By histogram, I just mean tell me how many zeros are there, how many ones, how many twos, etc. So let's just write a little bit of Python code to do that, because it's going to be a good motivator for dictionaries. So let me start by, so what do I want to do? I want to create a count of 10 numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so I'm going to initialize a counter list to be a bunch of zeros. So remember, the square bracket times notation says, please give me a list with 0 in it times 10. So a list with 10 elements, and all of them are 0. So it's just a shorthand notation of saying square bracket 0, comma 0, comma 0, comma 0, up until 10 of them. Okay, so I'm going to initialize this. And then in each entry here of counter list, I'm going to store how many zeros, how many ones, how many twos, etc. Obviously, where the digit corresponds to the index into the list. Okay, let's do that. For D and digits, digits is the list that has all the numbers that we care about. So D is now going to take on the value 0, 3, 2, 3, 4, 3, etc., etc. I'm simply going to reach into that element in the counter list and incremented by 1. So notice something cool here. D is the value of the digit, but it's also, by definition, the index into the list. So the 0th digit, the number of zeros is stored in the 0th position, obviously. The number of 9s is stored in the 9th position. And so I get to use the actual value as an index. And that distinction is going to become important in a minute. Okay, so I loop through here, going through all the digits. Obviously, that's big O of n because that for loop is running n times. And then I can, for example, print the counter list, and I will see how many zeros, how many ones, how many twos, etc. I've built a histogram. All right, so for example, you should be able to convince yourself that there's 4 zeros here. Here's 1, 2, 3, 4. And there's only 1 9. There it is right there. All right, now, imagine I wanted to look at a distribution of something a little bit different. So instead of numbers, I give you a passage. It was the best of times. It was the worst of times. It was the age of wisdom. It was the age of foolishness. Beautiful sentence, opening sentence. And what if I asked you to count up all of the wases? Okay. Now, just by way of motivation, this is one way that people do attribution of authors, is to look at things like how often do they use a word, or in what order do they use words, or is was followed by the more common than not common. And this is how one way that forensic analysts look at attribution. Did somebody write a particular document or a manifesto or something like that? Okay, so let's say I want to count up all the wases. Now, how did we do that in the previous iteration? Is I just indexed into a list with what I was looking for. But now what I'm looking for is not it's an integer. It's not 0, 1, 2, 3, 4. It's literally a word, a string. And this doesn't make sense, but that's sort of what we want, right? I mean, that was the really nice thing in the previous example, was that the value I was looking for and the index were the same, and so I could just keep incrementing the appropriate spot there. And so I sort of want to do this, but I can't. Not with a traditional list, but I can with a dictionary. Okay, so let's now talk about dictionaries. We are going, and I'm going to describe, again, in all detail, but let me just start with a little bit of Python notation. So dictionaries in Python are initialized with curly bracket. So lists are open square bracket, close square bracket. Dictionaries are open curly bracket, close curly bracket. Okay, so that is a dictionary. And a dictionary allows me to index on anything I want. So for example, notice here, I've initialized a dictionary to be my dictionary. Notice that the indexing is still being done with the square brackets, not with the curly brackets. That's only used on initialization, and then everything after that looks like a list notation. So my dictionary of blue is equal to 460. That is the wavelength in nanometers of this part of the visible spectrum. Not that it matters, but just so you know. So I can shove something into a list, now indexed not on positive integers, 0, 1, 2, 3, 4, etc., but on strings. That's sort of cool. How does it do that? Don't know yet, but we'll find out in a little bit. So I can also access elements based on an index. So if I ask for my dictionary of quote unquote, and notice that's a string. It's not a variable blue. It's the string blue. It will, of course, print 460. So I can assign anything I want into the dictionary. I can say my dictionary of blue is a color with wavelength of approximately 460 nanometers. And then when I print my dictionary of blue, it'll print now a string. So I can store a number in here. I can store a string in here, just like a list. So the only difference between a dictionary and a list, well, there's a couple of differences, but from your perspective as the coder, is what I'm allowed to index on now can be a string. All right, so here's the definition. A dictionary is a data structure that stores a relationship between key value pairs. By the way, that's what a list does too. It's just that the key is always 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In a dictionary, the key can be anything I want it to be. A key is an item used to index into the dictionary, taking the role of 0, 1, 2, 3 that we use for lists, and the value is just what is the information, what is the data that you are storing there. Okay? So that is a dictionary. It is a built-in data structure in Python. You don't have to implement it yourself the way we did with linked lists. All right, so let's look at a couple of examples and try to understand how exactly this is working. And then we'll get into the various algorithms and the runtime complexity. So let me define a wavelength dictionary to be an empty dictionary, open curly bracket, close curly bracket. And let me put 4 values into the dictionary, indexed on blue, orange, green, yellow, different parts of the visible light spectrum, with wavelengths 450, 600, 530, and 580. Okay, now let's just a couple of Python notations around dictionaries. So you will remember that for loops and lists had this very nice property where I could say something like for D in digits, where digits was a traditional list, and then D would take on every element of the list. For loops have a similar type of relationship with dictionaries. So I can say, for example, for key in wavelength dictionary. So wavelength dictionary is what I just defined. Key will then take on the values of blue, orange, green, and yellow. In the same, so a little bit different than what they did for a list. In a list, it would have taken on these values, but when we're indexing on a dictionary, when I say for key in the dictionary, it gives me the keys because these are no longer 0, 1, 2, 3, 4, 5. They're whatever we assign them to be. And then I can print, for example, key and then the value stored at the keyth entry in the wavelet dictionary. And of course, when I do that, I will get blue 450, orange 600, etc., etc. So there's that same relationship with for loops and dictionaries as we saw with for loops and with lists. All right. Now, I can do a couple of really nice things. I can find things in the dictionary with a little simple Python notation. So if I say blue in wavelength dictionary, it will return true because blue is a key. Notice here that both in this for loop and here, I'm indexing on the key, not on the value. So if I ask, is purple in the wavelength dictionary, it will say false because it is not keyed in here. So this in notation is a very easy way to figure out if you have a key associated with a particular string. All right, let's do another example. Same thing, my dictionary equals open curly bracket, close curly bracket, initialize an empty dictionary, shove 4 things into there, blue, orange, green, yellow, 460, 600, 530, and 580. And now let's think about how this is being done. Like, what is Python doing behind the scenes? This is a built-in data structure. So in some ways, I could just stop here and say, look, that's what you have. But we should understand this. We should understand how the dictionary is working. And in particular, what I eventually want to get back to is that find operator, because that was the motivating factor here, is how do you find things very, very quickly? Okay, so how would you implement this? If let's say dictionaries were not, in fact, built into Python, how would you do it? Well, here's one way you can do it. You could store in one list called keys, all your keys, blue, orange, green, yellow. So notice I've indexed these on 0, 1, 2, 3, because I've shoved them into a traditional list. And in another list called values, in the corresponding indices, I store the values, 460, 600, 530, 580. So I have 2 lists. You could, of course, put this into an object. And when I say my dictionary of green, I'll go along here, look for green, that's at index 2, go into values over here, go into index 2, and that is the value associated with the key green in the dictionary. Okay? So what would that look like if I want to do a find of an index? Well, I'd have to do linear search. Yeah? I'd have to start with the key. Let's say I want to find green. And I would start from the left, and I would say green, green. Ah, found it. And then I would get the index associated with that, and then I would go into values and get the value. Now that part's easy, because once I know 2, that's big O of 1, because random access in a list is big O of 1. But what's the runtime complexity of this? Well, that's going to be costly because I have to make my way through the list. So that, of course, is going to be big O of n. So we haven't really improved anything for finding. So we have this sort of cool structure that allows us to index into dictionaries with strings. That seems, you can imagine where that might be useful when what you want to index on is not always a number, but it's just something else. So that's sort of cool, but it didn't really help us with find, at least in the way that I've set up the data structure, where I have 2 lists, one of keys, one of values, and to find something, I have to do a simple linear search through that, or maybe they're in sorted order, but then I'm going to have to worry about inserting things in sorted order. So it's not really going to get me there. Okay? Now, in reality, that is not how dictionaries are implemented. They're implemented a little bit differently. And when we figure out how they're implemented, we're going to realize that find is much, much more efficient than linear time. So when we come back, let's look at the implementation of dictionaries, and then we'll look at the runtime complexity of find. So we'll be back in a few minutes.